In this video we're going to take a look at the anti-flag challenge on HackTheBox. It's an easy reversing challenge and the description says, flag, what's a flag? So we'll start by downloading the file and take a copy of it in our local directory. And let's go and do some basic file checks. So as usual, we'll begin by checking the file type, and we'll see that it's a 64-bit executable. It has Pi enabled, so we might need to bear this in mind if setting breakpoints that the program's going to load at a different memory address each time. And it's stripped, so we're not going to be able to see all the debugging symbols, function names, things like that. And since it's an executable file, we'll make it executable. And let's have a look at the strings. So we'll look for strings greater than 10 characters and just see if there's anything sticking out to us, any passwords or anything. This string looks interesting, and we have either a well done or a no flag for you, but we're not seeing too much. We know that the executable's been stripped, so we're not likely to see too much in there. So let's try and run the program. Try and run the program with no input, we just get no flag for you. Let's try and run it with ltrace, and we get well done, exited with status code 0. So depending on whether we run it with ltrace, let's try and run it again and enter in some parameters, and we just get the same response. How about without ltrace? And we get the same response. So we're going to need to go and take a closer look at the binary. Let's create a new ghidra project. I'll create a new project. I'll speed through this process because it takes a little while to set a new one up. So we have ghidra loaded up. We've got a decompiler on the right, our assembly code here, and then our functions and sections and stuff on the left. So we know that the program's stripped. It's not going to have a main function, but we can go straight to the entry function and see what function's called here, and this will take us through to the code that we're interested in. So the function's called with 6 parameters, and then we have this svar1, which is defined as the string length of this area of the .data section. If we go and have a look at that, we can see that we have some characters in here, some hex values, which presumably will be decrypted to give us our flag. And then we have this serial number as well, the string that we saw whenever we ran strings initially. And we can see down here then we have lvar2 is set to equal ptrace, and it's calling this ptrace command. Let's go and have a quick look at an article about anti-debugging. So this, I just found this is one of the first articles I found, just to give a quick overview. So whenever trace me is called, it will be able to determine if it's being run inside of a debugger essentially. So in this case that looks quite similar to what we have here. Let me go back. Our ptrace call is being called here, and if this comes back as -1, which is exactly what this is checking for, then it'll determine that in this case it prints out don't trace me. In our case it's going to print out well done, and then it's going to return 0. So essentially if we have a debugger running, if we're running this with ltrace or if we're running this in GDB or something like that, it's going to just print out well done and then exit the program. Otherwise, if we're not using a debugger, it's going to print no flag for you and then exit the program. So both essentially the same end result. It returns 0 and exits, but we get these different strings depending on that condition. So if we go back to this link, we can see that there are a couple of ways that we could solve this. We could look into patching the syscall with nops, the ptrace syscall. We could overwrite the ptrace function with a preloading by preloading a custom elf shared library. So maybe we'll look at this towards the end in terms of patching the binary, and we could also simply reverse this so that we're not checking for -1. So if it does equal -1, we could have it go to a different condition. So there's a variety of possibilities there. We could also, and the way that I initially solved this challenge was to run a debugger, and essentially whenever it gets to this check, we'll just skip past the check and skip to whatever section of the program that we're interested in. So it's not clear from here where we need to go, right? We have a condition and we have 2 possible outcomes. Neither one of them appears to get us any closer to printing out a flag. So at this stage I went and started looking through some of the other functions that we have here, these randomly named functions, to see if any of them would be of interest. But rather than decoding all of these, I returned back to the main function. So we'll go back to our main here, and if we compare some of the decompiled code that we have on the right to the assembly code on the left, it doesn't all quite match up. So we have the ptrace call right here, and it's returning, if it returns a -1 and that compare comes back true, it'll print well done, it'll put that out, and then it'll jump to leave and return, so it'll exit the program. However, If it doesn't equal -1, we're going to go down to this section here where it'll print out no flag for you, and again it'll put that out, it'll jump down to leave and return. But right before this no flag for you, we also have another comparison, which is comparing 539 in hex, which is 1337 or leet in decimal, and 9 as a character, and it's comparing that to RBP plus local 24 on the stack. So if we go and have a look at the beginning, we can see that these values are being placed onto the stack, and we have 1, 2, 3, 4, 5, 6, and we have here our 6 parameters. So presumably if we can line up our parameters correctly, we'll be able to ensure this condition is true, and depending on whether this condition is true will depend whether it'll jump down here. So this is another section of code that we haven't yet reached, and which if we actually have a look over here, we can't actually see it. So we could play around with some of these parameters here to see if we can pass in the right parameters to get this to line up with the correct value. The problem is going to be that if we want to debug that and actually see how they are lining up, whenever we run the program, this ptrace is going to come back with -1. It's going to print out well done, and it's never going to get down to that comparison, so we're never going to be able to check that. So I mean, we could do it. We could set it up so that we're changing conditions in the debugger or jumping past this condition. But probably the easiest way to do that in terms of debugging would be to patch the binary so that this ptrace isn't being called, or so that the result is being hard coded to a different value. But the way that I actually solve this, you'll notice that we have a removing unreachable block here. So some of the code's actually been removed because it can never be reached. So if we go to edit, tool options, and we'll go into decompiler and analysis, and we have this checkbox which is set to eliminate unreachable code. So if I untick that and click apply and then OK, you'll see that if we look at it now, we've actually got quite a bit more code here, and we can go and have a look at this section of code, which is the section of assembly that we were looking at before, but it's now being represented in the decompiled code as well. So we can see here then, if the ptrace comes back with -1, it'll print well done, and it'll just go straight down to exit. Otherwise, it's going to check if false equals true, which obviously false doesn't equal true. Then it'll call this function with these parameters, and then it'll put out this s parameter __ s. Otherwise, it'll print no flag for you. So again, now that we know that this is the case, we could go ahead and patch the binary so that this just always evaluates true, and then that would always print this out. The way that I solved this initially, I'm going to go through some different ways to solve this at the end, but the way that I initially solved this was to simply say, well, we can get the address of this, and although we aren't able to just set a breakpoint because pi is enabled, it's not giving us hard-coded addresses here, we can use the address offsets to calculate the offset from the pi base whenever the program's running. So the beginning of the lab we can see is right here, 1525, so that's where we're going to want to jump to. And what I'm going to do is I'm going to set a breakpoint somewhere around here before the jump not 0, and then we'll simply jump down to the address that we're interested in. So let me grab a copy of this offset 14F4, which is going to be this comparison check, and let's minimize this. We'll open up GDB-PwnDbg and pass in the file. PwnDbg, we can have a look at the functions here. It's stripped so we don't see our main function, stuff like that, although note that if we open up something like radar, we can have a look at the functions and we can see our main function here. We could select it and then disassemble it and have a look at the code in here, and also grab any offsets or breakpoints, things like that we're interested in. So we want to set up a breakpoint. The problem's going to be here, I can't just set up a breakpoint for an address because these are offsets. So if we wanted to try and set up a breakpoint, we can't just break at a function because we don't have the function names here. So what I'm going to do is I'm going to start the program and I'm going to tell it to break. If we use start I, it'll tell it to break at the first instruction essentially. Now the program's running, we can just run pi base to get the pi base, and then we know that the offset we're going to be interested in here was 1525, that's what we're going to want to jump to. So I'm going to grab that address now. We'll do pi base 0x1525. That'll give us the address of that function that we want to jump to get the flag. And now we want to just set up a breakpoint as well. I'm going to do break RVA, which will set a breakpoint at the offset that I provide here from the Pi base. And the offset is going to be this 14F4, 14F4, and I'm going to hit continue, just allow that to continue. It'll hit that breakpoint at the, you can see here, 54F4, and this is where it's going to do the jump not equals. Let's go back to the code for a second. So it's going to do the jump not equals here. Where is it here? Jump not 0, and we don't want it to do that because it'll print out well done and then exit the program. What we want it to do is just go straight down here. We don't want it to go to if false, because that's just going to say, well, false doesn't equal true, so exit the program. So we want to jump to right here, and we want to jump to right here, 1525, because it needs to set up all the variables and stuff first of all the registers. So that's good. We've got our let me grab that again, Pi base. I'm going to take a copy of this address, and then I'm simply going to say let's jump to, we'll give it an asterisk to denote it's an address, pass in the address, and then you'll see here that we print out the flag. So that was probably the quickest and easiest and laziest way to do that. Rather than going through and having a look at these functions, you can see we could go and try and actually reverse engineer these functions and see exactly what's happening in each of them, which I'm not doing. I'm kind of using the debugger to jump around the code, but a flag's a flag, and we've got the flag. But I will go through and have a look at patching the binary now as well, just to add a bit more content to the video. So we need to set up ghidra in order to patch binaries. Let me open up this article. I'll leave a link to this in the description, which talks about what we need to do. So this gives quite a good example about patching a binary. In this case, they are taking, or in this case here, they're taking the jump not 0, and they can change it to jump 0. So you can see here the difference between the opcodes here. We have 740C and we have 750C. So it'd be quite easy for us to, if we go back to our if false here, we have it's jumping if 0. So it'd be quite easy to change a 74 to a 75, and then just write in that to the binary so that every time this runs it'll check if true equals true. And similarly, we could do something like that around here as well. This is a compare instruction, but we could be comparing it to a different value. Or we could, as was mentioned, we could patch out the ltrace call altogether with no operation instructions. So there's a few different ways we can do that. We need to, let's go and see about saving the patch here. So to save the binary, we can use this save patch. So let's go and have a look at the GitHub for this. And it says this is a workaround that addresses some issues in ghidra that ghidra has around saving patched binaries. So I was looking into this the other day, and there is, I think, the official response from ghidra, or I guess the NSA, was to say that you can either build a custom branch and make some changes to it, or you can just use the save patch script, which seems a bit easier. So let's get that set up instead. So we'll go and download a copy of the save patch file to our local directory. And if we go back here and see what we need to do, then we need to go and create a new script, and let's go and do that now. And if we go to create a new script here and select Python, and I'll just call this new script, you see the directory has automatically been created and enabled for use, and it gives us this directory. Now I tried using this directory and I couldn't get it to actually display anything in there, so instead the option that I took was to, let's just look for the current directory. So I'll search for ghidra scripts, and just basically took this directory here, so the features Python ghidra scripts. So I'm going to take a copy of that, and I'm going to move the save patch to that directory. And if we go back here to our script browser, let's have a look for save patch. It's not there. Let's try and refresh, and now we have it. So if we go back to our article, so we can see here that to use a script and save patch instructions, we select patch lines in the listing window. Since it does not allow saving multiple patches at the same time, you have to make all modifications into one patch. So when patching multiple instructions, you need to select everything from one patch instruction to another patch instruction, and then run the save patch.py script. So essentially, if we are, in this example, we're going to change this if false to if true. So instead of it running through and every time checking if false equals true, it's going to check if true equals true. And that's going to involve changing this jump 0 to a jump not 0. But if we also wanted to change, for example, this jump not 0 to a jump 0, then we would have to make the changes and we'd have to make sure that all of this is highlighted. We can't just highlight the individual instructions that we're changing before we go to patch it. So it has to be all part of one patch. So for now we want to change this jump 0 to the jump not 0. The only thing that's going to change is a 7.4 is going to change to a 7.5. So let's go ahead and do that. If we right click it, we can go to, where is it, patch instruction, and we'll hit OK there, and then we'll just go ahead and just add this n there to make that jump not 0. You can see it's updated to 7513, and here you can see now it's checking if true equals true, it's going to print out the flag. So providing that we're not debugging it, if this doesn't come back with -1, it's essentially going to check if true equals true, print out the flag, and that should just give us the flag just from running the program without any parameters and without any debugger attached to it. So let's go ahead and try and see if we can save this then. So let's update our jump not 0, which is right here. Select it, and now we want to go to our script, save patch, and we're going to run that. Oh, yep, save patch is running. And where do we want to save the changes to? So let's go to the same directory that we're in. I'm going to go to HackTheBox Reversing, and we'll call this true flag. You can see that it saved that. So let's go and have a look at the file. We can check the file type, make sure everything's looking okay. I'm not sure if it's already executable. Let me make it executable just in case. And now let's just try and run it. So we run it and we get our flag back straight away. So if we run, let's remind ourselves, if we run anti-flag, we get no flag for you. If we run ltrace anti-flag, we get well done. And we're going to get the same thing if we run that with true flag, presumably here as well. We get well done. But if we run it, yeah, without ltrace, then we'll get our flag back. So while we're looking at patching binaries, why don't we also patch out the ptrace call as well, so that whether we're using a debugger or not, it'll still work for us. So what I'm going to do is I'm going to create, rather than doing this in ghidra, let's try out a different tool. We'll use PwnTools to patch the binary this time. So I'm going to import everything from PwnTools. We'll set up our file here. So our executable is, we could read in anti-flag, but I'm going to read in the true flag because we've already patched that other condition. Let's just patch out this second condition so that regardless of whether you run it in a debugger or not, it's going to come back with the flag. So we'll say xe is equal to true flag. We'll set our elf here, so we can set the context binary just so that it knows. It's probably not going to be an issue here, but it's always a good habit to get into. This will mean that every time you make some changes, for example, if you're writing a payload or something like that, then the addresses will be in the right format for this binary. So it'll be, in this case, 64-bit, it'll be least significant bit, etc. So we can also turn off checksec as well, so we don't want to call checksec. So we'll do that. We want to patch out ptrace, so what I'm going to do here is just put elf asm, and you can see here that the ASM is going to take in an address and then some assembly instructions to write over that address with. The address that we want to overwrite is the ptrace. So let's go back, actually, let me just quickly go back to open up GDB-PwnDbg, and we'll open up true flag. If we go in here and just have a look, info functions, we'll see that we have the ptrace function. So we could provide, well, we can't provide this address because this is an offset, so we would need to run the program first and calculate the pi base, I believe. I'm not actually too sure, actually. Maybe you could do that. But let's just go ahead here and we can just say elf.symbols because we know that this is a function there, and then we can pass in ptrace. You can do this in either syntax, so you can just do it like this as well. Ptrace, and what do we want to replace it with? I'm just going to replace it with a return instruction, so it's basically going to do nothing. And then we want to save this patched binary to a new file, so we'll do elf save, and I'll just call this hacks flag. Let's try and run that. Python patch. It runs, and now presumably then let's just remind ourselves, if we go back to our true flag, we run it, we get our flag, but if we run it with ltrace, it's going to say well done. So what about our new file? If we do chmod plus x on hacks flag, and now we try to run it, hacks flag, it should print out the flag, which it does. What about if we try it now with ltrace on after patching out that function call? And you'll see that we get our flag back. So now, whether you run it with a debugger or not, all you have to do is run the program to get the flag back. And that's been the anti-flag challenge. I hope you've enjoyed the video. If you have any questions or comments, leave them down below. Thanks.